I'm Algebra Annie, and I'm here to help you be successful in your algebra class. Some days you just have to create your own sunshine. Sam Sundquist. Our learning targets today are: I can write the prime factorization of numbers. I can find the GCF of monomials.
Now we are looking at factors and greatest common factors. And we're going to begin by looking at what exactly is a prime number. According to our math dictionary, a prime number is a whole number greater than 1, and it has to have exactly two positive factors, 1 and itself. So what is a prime number? Basically, if you can break a number up into itself and 1, it's a prime number. So let's go ahead and list a couple of examples of prime numbers. It says it needs to be greater than 1. 1 is not a prime number. Our smallest prime number is 2, because the only way to get 2 is to multiply 1 and 2. The next is 3, because the only way to get 3 is to multiply 1 and 3. We have 5. 6 is not a prime number, because you can do 1 times 6 or 2 times 3. 6 is not prime. We've got 7. 8 is not prime, because I know 2 times 4 is 8, so that doesn't work. 9 is not prime, because I know 3 times 3 is 9. We've got 11, 13, and the list goes on. So this is the first few prime numbers that we should know. Another word that we need to know is factors. Factors are numbers that are multiplied to find a product. So factors are things that multiply together to give us a number. A number is divisible by its factors. So they want us to write the prime factorization of 60. And I noticed that I have 60 here twice. It's because I want to show you something. So we're going to split it right down the middle. I'm going to solve the problem first. In a prime factorization, to figure out what it is, we're going to do a factor tree. This is why we learned what factors were. It says that it's numbers that are multiplied together. So I need two numbers that multiply together to give me 60. Any two numbers. So 6 and 10 could multiply to give me 60. Is 6 prime? If it is prime, then I am not able to break it up. 6, however, is not prime, so I can break it up again. 6 is 2 times 3. Is 2 prime? 2 is prime. I cannot break it up to two other factors. So 2 is prime. That's the end of that branch. Is 3 prime? 3 is. That's the end of that branch. I ended all my branches. Got to come over to the other branch. Is 10 prime? 10 is not prime because I know that I can break 10 up into 2 and 5. 2 is prime, so that branch ends. 5 is prime. That branch ends. This is what we call a factor tree. For many students, the factor tree helps you find the prime factorization. 2 times 3 times 2 times 5. These are all the prime numbers that you would multiply together to give you 60. So I know that 60 is the same as 2 times 3 times 2 times 5. This is the prime factorization of 60, except for we're in algebra, we're in high school now. We don't do the little x's for our time signs, and these should in theory be written in numerical order. So this should be written as 2 times 2 times 3 times 5. This is the correct prime factorization. There is a shorter way that you can write it. Notice that I have 2 here twice. So we're going to apply our exponent rules. I see that the 2 was twice times 3 times 5. This is the official prime factorization that we need to make sure that we know how to do. Now we had it again. Over here, our first breakup was 6 and 10. What if you couldn't come up with 6 and 10? What if you came up with a different one? What if I came up with like 2 and 30? That's fine. You can still do it the same exact way we did this factor tree. So 2 is prime. That branch ends. 30 is not prime. He can be broken up. 30 is broken up into 3 and 10. 3 is prime, so that branch ends. So now I'm on to 10. 10 is not prime. 10 can be broken up into 2 and 5. 2 is prime. 5 is prime. So I finished my factor tree. Well, now what? I need to find the prime factorization. So I know that 60 is 2 times 3 times 2 times 5. But these are supposed to be written in numerical order. So 2 times that 2 times 3 times 5. But I know my rules of exponents. This can be written shorter. 2 is multiplied twice. times 3 times 5. This is the prime factorization. Notice I used two different factor trees, but I still got the same answer. It does not matter what your factor tree looks like. In the end, we all come down to the same answers. So if you did your factor tree different than your friend, it's fine. Your answers should still be the same. Now the factor tree is really important in order to get a prime factorization if our numbers are getting really big. So we're going to practice a few more times. 40. How can I break up 40? Well, I know that it ends in a 0, so I know I must be able to multiply by 10. So 4 times 10 is 40. 4 is not prime, so I need to break 4 up into two numbers, which is 2 times 2. 2 times 2 gave me 4. 2 is prime. 4 is prime. Those branches end. So I had to come over here and I have to finish the 10. 10 is not prime. 10 can be broken up into 2 and 5 because 2 times 5 is 10. 2 is prime. 5 is also prime. All of my branches ended with a prime number. So I'm done with my factor tree. So if I'm trying to find the prime factorization for 40, that's 2 times 2 times 2 times 5. I can write this shorter. There were 3 of them. So 2 is multiplied together 3 times, and then that was multiplied to a 5. This is the prime factorization of 40. Let's go ahead and do it for 33. I need two numbers that multiply together to give me 33. I know 3 times 11 would give me 33. 3 is prime. 11 is prime. So it was really short factor tree. 33, the prime factorization is 3 times 11. And that is the prime factorization of 33. Now we have a few more definitions that we need to learn. Factors that are shared by two or more whole numbers are called common factors. So they were factors that numbers shared. They were all the factors that the numbers had in common. They're called common factors. If it is the largest of those common factors, we call it the greatest common factor. And you may be familiar with our shorthand of saying greatest common factor, GCF. So if you can find any factors that numbers have in common, they're the common factors. And if you can find the one biggest one, he is the greatest common factor. So let's find the greatest common factors between the numbers 24 and 60. Well, I don't know what my prime factorization is, so I need to come up with a factor tree. So here's my factor tree of 24. What two numbers multiply to give me 24? Well, I know 8 times 3 gives me 24. 8 is not prime. 8 can be broken up into 2 and 4. 2 is prime. 4 is not. 4 can be broken up into 2 times 2. 2 is prime. 3 is already prime. So this is my factor tree for 24. So looking at this, I know that 24's prime factorization is 2 times 2 times 2 times 3. Well, now let's go ahead and do this to 60. I need two numbers that multiply together to give me 60. Well, I know 6 times 10 is 60. 6 can then be broken up into the factors of 2 and 3 because 2 times 3 gives me 6. 2 is prime and 3 is prime. That branch ends. Now I need two numbers that multiply together to give me 10. 2 and 5 both multiply together to give me 10. 2 is prime, 5 is prime. So looking at this, I see the prime factorization for 60 is 2 times 2 times 3 times 5. Now I want to know what is the greatest common factor. So if we're going to find our GCF, what numbers do they have in common? I see that each row has a 2, so I'm going to take that 2 out. I'm going to put that 2 right down here and say that's part of my GCF. Now I'm going to multiply that by, are there any other numbers in common? I see another 2, so I'm taking that 2 out of my list and I'm going to put it down here in the GCF because they had that number in common. Are there any other numbers in common? There are, so I'm going to multiply by, I see a 3, so I'm going to pull that 3 out. The 3 is going to go down here into the GCF. They had a 2, another 2, and a 3 in common. What is 2 times 2 times 3? Well, 2 times 2 is 4. 4 times 3 is 12. So I have 12 being the largest factor between 24 and 60. We're going to really need to know this for tomorrow's lesson, so we're going to practice it a few more times. I need to find the prime factorization of 18 and the prime factorization of 27, and then find which GCF they have between the two of them. So let's make our factor tree for 18, and then we'll do a factor tree for 27. There's me splitting my paper. So my factor tree for 18. I know that 9 times 2 is 18. 9 is not prime. 9 can be broken up into 3 times 3. The 3's are prime. 2 is also prime. So my prime factorization for 18 is 3 times 3 times 2. That's not technically written correctly. Prime factorization should be written in numerical order, so it's 2 times 3 times 3. So that's my prime factorization for 18. What is the prime factorization of 27? I know that 9 times 3 is 27. 3 is prime. 9 is not. 9 needs to get broken up. 3 times 3 gives me 9. 3 is prime. 3 is prime. So I know that the prime factorization for 27 is 3 times 3 times 3. So the prime factorization for 18, the prime factorization for 27. Now it's a little hard for me to kind of read them this way, so I would like to write them so that they are on top of each other. So here's my prime factorizations written on top of each other. So comparing 27 and 18, I am looking for the GCF. What numbers do they have in common? I see that they each have a 3. So I'm going to pull the 3 out of their lists and say, hey, you're down here my GCF now. You had that number in common. I see another 3 in each list. So I'm pulling that 3 out and saying, hey, there's another one that I have in common. They have no other numbers in common. So 3 times 3 is 9. So the greatest common factor between the numbers of 27 and 18 is 9. So let's go ahead and come over here and we're going to do it again. We're going to do it for 12 and we're going to do it for 16 and see what the greatest common factor is between those numbers. What two numbers multiply together to give me 12? I know 6 and 2 multiply to give me 12. 6 is not prime. 6 can be broken up into 2 times 3. 2 is prime, 3 is prime, and 2 is prime. So I'm done with 12. The prime factorization for 12 is 2 times 2 times 3. Now knowing in advance, I like them written up and down, one on top of one another, vertically. So whatever the prime factorization for 16 is, I'm going to put it right below the 1 for 12. So what two numbers multiply together to give me 16? I know 4 times 4 give me 16. 4 is not prime. 4 can be broken up into 2 times 2. 2 is prime. 2 is prime. 4 can be broken up again into 2 times 2. 2 is prime. 2 is prime. So the prime factorization for 16 was 2 times 2 times 2 times 2, because I see them right there. Now I need to find the GCF. What numbers do these lists have in common? I see they share this 2, so I'm pulling them out, and it's going to go down here in my GCF list. I see another 2, so I'm going to pull them out. It's going to go right down here in my GCF list. There are no other numbers that 12 and 16 have in common. So 2 times 2 is 4. The greatest common factor between the numbers 12 and 16 is 4. Now how do you do this when they bring in the variables, the letters? You're going to treat it the same exact way. You already know how to do this. So we need to find the prime factorization for 3x to the third. Prime factorizing 3, it's just 3 because it's prime. What is the prime factorization of x to the third? That means x times x times x. So 3 times x times x times x are all the individual factors for 3x to the third. What are the individual factors for 6x to the second? You need to prime factorize 6. Prime factorizing 6 is 2 times 3. X to the second is x times x. Now if you have a hard time prime factorizing the number in your head, use your factor tree. So if we had a factor tree 6, what two numbers multiply to give me 6? I know that 2 times 3 gives me 6. 2 is prime, 3 is prime. 2 times 3 was my prime factorization, if you struggle. Now I need to find the GCF. I see that they have a 3 in common. So I'm going to pull that 3 out of my list. 3 comes down here. He's part of my GCF. I see that they share a x. So I'm going to pull that x out. That x comes in here. He's part of my GCF. I see that they share. So I see they have another x in common. So I'm going to pull that x out. And that x is now down here. And it's in my GCF. I see no other numbers or letters in common. Up here, I've only got one x left. There's no other x down here. Down here, I see a 2 left. There are no other 2's. So I've pulled out all the things that are in common. So what was my GCF? Multiply all the numbers. It was just 3. X times x is x squared. So I know that the GCF between 3x to the third and 6x squared is 3x to the second power. That is my GCF. Let's come do it again. Now let's pretend I do not know how to prime factorize 18. So we're going to use a factor tree. I know that 2 times 9 is 18. 2 is prime. 9 is not. 9 can be broken up into 3 times 3. 3 is prime. 3 is prime. I just found the prime factorization for 18. What is the prime factorization for 27? I don't know, so we got to break it up again. I know that 9 times 3 gives me 27. 3 is prime. 9 is not. 9 can be broken up into 3 and 3. So I just found the prime factorization for 27. So 18g squared. Breaking up the 18, it's 2 times 3 times 3. So 2 times 3 times 3. The g squared meant you multiply g twice. Let's break up the 27g to the third. 27 was 3 times 3 times 3. So there's my 3 times 3 times 3. G to the third meant you had 3 g's multiplied together. So let's go ahead and look at the GCF. I see that they have a 3 in common. So I'm pulling that 3 out of my list. He goes down here. He's now in my GCF. I see another 3 in common. So I'm pulling that 3 out. He now goes down here. He's part of my GCF. There are no other numbers shared in both lists. So now I go to my letters, my variables. I see a G here. So pull him out. He's part of my list. I see another G. Pull him out. He's part of my GCF list. I see no other letters, no other variables in common between the top and the bottom list. So I have all my parts. So what is my GCF? 3 times 3 is 9. G times G is G to the second power. So my greatest common factor between 18G to the second and 27G to the third is 9G to the second. So our last problem for the day, Samantha is making beaded necklaces. And she's got 2 different types of beads. She has glass beads, and she has 54 of those. And she has clay beads. She has 18 of those. How many beads does she actually have together? So how many beads does she have total? Well, there were 54 glass beads and 18 clay beads, so a total of 72 beads. So she has 70 beads total. She wants each necklace to have the same number of beads, but each necklace can only have one type of bead, meaning you're either going to have a glass bead necklace or a clay bead necklace. You cannot mix them. If she puts the greatest possible number of beads on each necklace, how many necklaces can she make? Well, first, what is the greatest possible number of beads that she can put onto each necklace? So we need to find the GCF. So it's first asking us, what is the GCF? So I want to find my GCF between the 54 glass beads and the 18 clay beads. So what is my GCF? So 54, because I don't know that number, can be broken up into, well, I know 2 times 27. It ends in an even, so I know 2 had to go in, so I use my calculator. 2 is prime. 27 can be broken up into 9 and 3. 3 is prime. 9 can be broken up into 3 and 3. Now I've got to do 18. 18 can be broken up into 2 and 9. 2 is prime. 9 can be broken up into 3 and 3. So I now have my prime factorization lists, and we're going to use those to find the GCF, because we're not done. So 54 was 2 times 3 times 3 times 3. 18 was 2 times 3 times 3. So I'm looking for my GCF. So looking at the factors that both lists share. I see a 2, so I'm going to pull it out. I'm going to put a 2 in my list. I see a 3. I'm pulling it out. There's a 3 in my GCF list. I see another 3 that they share. Pull it out. There's a 3 in my list. There is no other number in common between 54 and 18. So 2 times 3 times 3, which ends up being 18, is my GCF, meaning the greatest number of beads on each necklace is going to be 18. I have 18 beads on each necklace. But that's not the question. How many necklaces can I make? If I have a total of 72 beads, and I'm going to break that into necklaces of 18 each, how many necklaces am I going to get? So how many necklaces can I make with 72 beads if I know 18 are going to be on each necklace? Well, I'm going to take my 72 beads and I'm going to divide it by 18, and you end up getting 4. So I'm going to get a total of 4 necklaces. And I'm done.
What did we learn today? I can write the prime factorization of numbers. I can find the GCF of monomials, and I look forward to seeing you tomorrow in class.